Welcome to another video lecture. In this video lecture, we will discuss the different parameters for the time response of second order system in the underdamping case. Now, in the last lecture, we derived this expression for the response of the second order system. Ct is equals to 1 minus e raised to power minus zeta omega n t divided by 1 minus zeta square root into sine omega dt plus theta, where theta is given by this expression. Now, if you plot this response Ct with respect to time, let me plot this here. We take time as the horizontal axis and the y-axis is Ct. I am plotting this for different values of t. So this graph will start from t is equals to 0. The value at t is equal to 0 will be 0. The maximum value, or you can say this graph will oscillate, since there is a sinusoidal term here, so this will oscillate around this value 1, which is also the steady state value. So this value is 1. So this graph will start from this position, t is equals to 0, and it will oscillate in the sinusoidal manner, and at each iteration the amplitude will keep on decreasing till at t is equals to infinity it will be 1, like this. So for this response of the second order system, we will define few parameters. The first parameter is the peak time. So let me write here peak time, denoted as Tp. So the peak time is the time when the response gets its maximum value. So here in this graph you can see this is the maximum value. So the time required to achieve this maximum value is the Tp. So this value of time on the horizontal axis, this is the peak time, Tp. The second important parameter is the maximum overshoot. Now this value maximum overshoot is the maximum value which the response get from the steady state value. So this is the steady state value 1. So the maximum value of the response from the steady state value is the maximum overshoot, denoted by MP. So this value here is the MP. The third parameter is the rise time, denoted by TR. So rise time, for now especially we are discussing this for the underdamping case. So for the underdamping case, rise time is the time required for the system when it goes from 0% to 100%. Time required for a system to go from 0% to 100% is the rise time, especially for the underdamping case. So response is 0 here, and rise time 100% of the steady state value. So rise time is the time required for the system to go from 0% to 100% of the steady state value. Now steady state value is 1. So here the steady state value at origin is 0, and here the steady state value is 1. So this time required from this to this, from 0 to 100%, is the TR, the rise time. Now the fourth parameter is the settling time. Settling time, TS, denoted by TS. Now the settling time is the time required by the output to settle down within plus minus 2% of the tolerance band. So what exactly is the tolerance band? Since this value here is the steady state value 1. Now within this steady state value there is a tolerance limit where the value of the output lies above this value, steady state value 1, and below this steady state value. So if this value lies within 2% of the tolerance limit, the response till that time is known as the settling time. So this time from here to here until when the response is plus minus 2% of the tolerance band is the settling time, TS. So we will determine all these parameters: the peak time, maximum overshoot, MP, rise time, TR, settling time, TS, for this second order system in the underdamping case. Let us first derive the expression for the peak time. So first is peak time denoted as Tp. Now the expression for the response Ct is given by Ct is equals to 1 minus e raised to power minus zeta omega n into t, 1 minus zeta square sine omega d t plus theta. Now if you can remember, this is the response. Now this is the peak time. This is the peak time from the time required for the system to get the peak value. Now at the peak value, we get flat slope. The slope, the value of tan theta, or the slope at the peak time, will be 0. So let me write it here. At t is equals to Tp, the slope of Ct becomes 0. So I can write it, slope can be determined by differentiating Ct with respect to t. Slope at t is equals to Tp becomes 0. So I will use this fact and determine the value of Tp. So I will differentiate this expression with respect to t, and then I will put t is equal to Tp to get the value of peak time. So I am differentiating. Let me put this equation as 1. Now differentiating equation 1 with respect to time. So this will be 0 minus the differentiation of this e raised to power minus zeta omega n t is the zeta e raised to power minus zeta omega n t multiply by minus zeta omega n divided by 1 minus zeta square. The differentiation of this will be remain as it is, sine omega dt plus theta minus e raised to power minus zeta omega n t will remain same, divided by 1 minus zeta square. This time we will differentiate this, so this will be cos omega dt plus theta, and this will be multiplied by omega d. This will be multiplied by omega d. So let me solve this further. So let me solve. So we can take these two terms common here. So these two terms will be common. So e raised to power minus zeta omega n t divided by 1 minus zeta square I can take common. So this will multiply by this, minus minus will be plus. So inside I'll get zeta omega n into sine omega dt plus theta, and this will be minus omega d. I can write omega n 1 minus zeta square divided by, so this zeta square I have already taken outside, and this will be cos omega dt plus theta. I can take omega n also common, so this will be omega n, and this term will go into 0 on the, this will be 0, the right hand side term is 0, so this will go into 0. So this will be zeta sine omega dt plus theta is equals to 1 minus zeta square root cos omega dt plus theta. So I can take this ratio to get the value tan theta here. So let me move to the next slide. So I can write here tan theta, omega dt plus theta is equals to square root 1 minus zeta square divided by zeta. So let me go to the previous slide and confirm this is correct. Yes. Okay, if you can remember, in the derivation of Ct, we have assumed a right angle triangle in which this angle is theta. This is 1 minus zeta square, this is 1, and this is zeta. In this triangle, the value of tan theta was 1 minus zeta square divided by zeta. So I can write this value is equals to tan theta. So tan omega dt plus theta is equals to tan theta. So from trigonometry, I know that tan n pi plus theta I can write it as tan theta. So if I compare these two equations, I can write omega dt should be equals to n pi then. So in this case, since this t is Tp, so this t is Tp, since at t is equal to Tp, the slope was 0. So now I can write Tp as n pi by omega d, where omega d is omega n 1 minus zeta square. So now what is the value of n here? Since we are talking about the first maxima, Since, let me again write it, since the slope will be 0 at each maxima, but I'm talking about the peak value will be the first maxima, so here the value of n should be 1. So in this case, the final expression for the peak time will be pi divided by omega n 1 minus zeta square. So this will be the value of peak time. So I hope you understood this. The next parameter is maximum overshoot. So let me first define what is the maximum overshoot. So this is the response Ct of the second order system. This is steady state error 1, and the response which we get is the damped oscillations in the underdamping case. So these are the damped oscillations we get, and this is the peak value which we get, the maximum value which we get at Tp, which we defined in the previous slide. So this is the peak time Tp, and at this peak time we get the maximum value. So this is the maximum value of the output. So this is the maximum value. Now the maximum overshoot is the value which we get from subtracting this maximum value from the steady state value. So this value here, this value is the maximum overshoot MP, which we get from the maximum value. This is the maximum value minus 1, which is the steady state value. So mathematically I can say that MP is nothing but Ctp, which is the maximum value of the response, minus the steady state value 1. Now I already know that in previous slide we already determined this value Tp. It is equals to pi by omega d, or you can say it is pi by omega n under root 1 minus zeta square, and its value of Ct, the response of second order system in the underdamping case, is 1 minus e raised to power minus zeta omega n t divided by 1 minus zeta square sine omega d t plus theta. Now we can put this value Tp instead of t to get the maximum value. So let me define this here. Ctp is equals to 1 minus e raised to power minus zeta omega n into Tp divided by 1 minus zeta square sine omega d Tp plus theta. Now put this value Tp in this expression here. So let me write it here. Ctp further is equals to 1 minus e raised to power minus zeta omega n, and value of Tp is pi by omega n 1 minus zeta square divided by 1 minus zeta square sine omega d, and this time I am putting this value in the form of omega d. So this is pi by omega d plus theta. Now here this omega n and omega n get cancelled, and here omega d and omega d get cancelled. So this value comes out to be 1 minus e raised to power minus zeta pi divided by 1 minus zeta square divided by 1 minus zeta square into sine, this will be pi plus theta. Now we know that sine pi plus theta, we know that sine pi plus theta is minus sine theta. So let us move to the next slide. So finally Ctp is equals to 1 minus e raised to power minus zeta pi divided by 1 minus zeta square divided by 1 minus zeta square. This will be sine pi plus theta is minus sine theta, so this will be plus here. So this is the final value of Ctp, and we know that MP, as we already defined, it is Ctp minus 1. So this will be 1 plus e raised to power minus zeta pi divided by 1 minus zeta square divided by 1 minus zeta square into sine theta minus 1. This again, this one and this one will get cancelled. So this will be e raised to power minus zeta pi divided by 1 minus zeta square root divided by 1 minus zeta square root into sine theta. Now, if you can remember the right angle triangle which we defined in the derivation of the response of underdamping case, this angle was theta, this hypotenuse is 1, the base was zeta, and the perpendicular was 1 minus zeta square. In this right angle triangle, the value of sine theta is equals to 1 minus zeta square root. Now, if I will put this value here, these two values will get cancelled. So, finally, the value of maximum overshoot comes out to be, so value of maximum overshoot comes out to be MP is equals to e raised to power minus zeta pi divided by square root 1 minus zeta square, 1 minus zeta square. So, this is the value of MP, or the maximum overshoot, for this underdamping case. Now, generally we calculate this value MP in percentage. So, when we calculate this value in percentage, then this factor will be multiplied by 100. So, MP in percentage is equals to e raised to power minus zeta pi divided by square root 1 minus zeta square into 100. So, the next parameter is the rise time. Rise time is basically time required for the response to rise from 0 to 100% of the final value, which is the steady state value. So, in this case, the final value or the steady state value is 1. So, the time required for the response to rise from 0 to 100% of this final value is the rise time, and this is for the underdamping system. Now, to calculate the rise time, as we know that from the definition, at t is equals to tr, the value of Ct should become 1. So, at t is equals to tr, the value should of the rise of the system response should become 1, which is the final value, which is the 100% value of the steady state value. So, at t is equals to tr, Ct should equals to 1. So, let us put this value. So, Ctr is equals to 1 minus e raised to power minus zeta omega n tr divided by 1 minus zeta square root into sine omega d tr plus theta, and this value should equals to 1. Now, these two values 1 and 1 get cancelled. These all parameters will cancelled if we take these parameters common. So, finally, I can say that sine omega d tr plus theta equals to 0, and sine theta is, I can write it as omega d tr plus theta should be equals to n pi, and with this I can calculate value of tr is equals to n pi minus theta divided by omega d. Now, the value of n should be 1, so that I can get, let me draw the response to understand this. This is the response of the second order system, this is the steady state value, and we are getting the damped frequencies like this. So, the value of tr is the first time the value attained 1. So, this is tr, the first time it attains this value 1, the system attains value 1. In how much time it attains this value 1 from 0 to 100% of this final steady state value. So, for this the value of n is equals to 1. So, I can say that finally that value of rise time is pi minus theta divided by omega d. Omega d is omega n 1 minus zeta square. So, this is the value of rise time. So, the final parameter is settling time. Settling time is basically time required by the output to settle down within plus minus 2% or plus minus 5% of the tolerance band. Now, what exactly is the tolerance band? Now, this is the steady state value of this second order system in the underdamping case. So, this value is 1, the steady state value. Now, around this value we have tolerance band. Either we can have a plus minus 2% tolerance band, which is the values plus minus 2% of this steady state value, and either we can have plus minus 5% tolerance band, which is the values near about plus minus 5% of this steady state value 1. Now, in how much time the system attained these tolerance band is the settling time, either 5% tolerance band or either 2% tolerance band. So, this is the settling time Ts. Now, to calculate the value of Ts, we have to make some approximations because after settling time or when the system gets settling time, the oscillations vanishes and the system response is purely exponential. So we will derive this value of settling time by assuming that the response is purely exponential, like 1 minus e raised to power minus zeta omega n into t, and at t is equals to ts, the value is 2% of the settling time, so it comes out to be 0.98. Now with this equation we can calculate the value of Ts by taking log on both the sides. So the final value comes out to be equals to approximately 3.912 divided by zeta omega n. Here zeta omega n is the time constant, T time constant of the second order system. It is the time constant of the second order system. So I can approximately write that Ts is equals to 4 into T, where T is the time constant. Similarly, if we get the 5% tolerance band, the value of Ts comes out to be approximately, it is 3 into T, where T is the time constant. This is for 2% tolerance band, and this is for 5% tolerance band. So these are the 4 parameters which we derive in this lecture. The peak time, let me write all the expressions here. Peak time, Tp is equals to pi by omega d. Second parameter we derive is the MP, which is e raised to power minus pi zeta divided by 1 minus zeta square. Third parameter we derive is the rise time, Tr is equals to pi minus theta divided by omega d, and the final parameter is the settling time, equals to either 4 into T or either 3 into T, where T is the time constant, equals to 1 by zeta omega n. Thank you.